Hello, math loving person. So this video, we're gonna prove that that the derivative of e to the x is equal to e to the x. In order to understand this proof, so again, we're going to use that definition of the derivative, the limit as h approaches 0 of f of x plus h minus f of x over h. But before we do that, to prove this, we need to just do a little bit of preliminary work. So just a reminder from pre-calculus, and actually this might not feel like a reminder because I'm going to write this differently now that we have limit notation. So most people start working with the notation for limits in calculus and not necessarily pre-calculus. But you do get this definition in pre-calculus. It just doesn't look like this. It looks different from this. And it's just that e, the number e, that's Euler's number. It's actually defined as a limit. So it's basically the limit of 1 plus 1 over, I'm going to use a capital N, even though usually like you'll see lowercase n's here. I'm using a capital N just because I don't want to confuse my lowercase n with an H. They kind of look the same. So in pre-calculus, like maybe, I don't know, maybe you spend some time like plugging in larger and larger values of n into this expression, 1 plus 1 over n raised to the power of n. This expression, that gets used for compound growth, compound exponential growth. And so if you just like imagine like plugging in like larger and larger numbers for n, I will show you how many, that's 4 zeros, this is 5. Okay, so we'll just go up to that, right? So if you just imagine plugging in larger and larger numbers for n, so like for the first one, when I plugged in 100 for n, I get about 2.7048. And then when I plug in 1000 for n, that's 1.001 raised to the power of 1000. I get about 2.7169. And then when I plug in 10,000 for n, I get about 2.718. 1. And then when I plug in 100,000 for n, I get about 2.7183. The larger I go, 1, 2, 3, 4, 5, 6, I have 6 zeros. So like the larger I go, the closer I get to this number e, basically. So when I plug in 1 million for n, I get 2.7183 again. So I'm getting these numbers. So here I am, I was just using my calculator. I was plugging in these various numbers for n. And then notice on my calculator, if I enter the number e, just e to the first power, look at, it's like really close to these numbers, right? So this number, is defined as a limit. It's the limit as n approaches infinity. You get closer and closer to e, about approximately 2.718. So keeping that in mind, we're going to keep this in mind. What we're going to do is we're going to call, this is just for our purposes, we're going to call h, I'm sorry, we're going to call 1 over nh. Okay. So, so if I've decided to just refer to my 1 over n as h, what that means is as n approaches infinity, so if we have n approaching infinity, 1 over n h, which is equal to 1 over n, is just approaching 0. It's getting smaller and smaller. Because if you imagine, again, you can imagine, here's h. If we let n get larger and larger, so like if n is 100, for example, 1 over n is going to be just 0.01. If n is 1,000, 1 over 1,000, that's 0.001. If n is 10,000, 1 over n is 0.0001. So you guys get the idea. The larger n gets, the smaller 1 over n gets. It just gets closer and closer to 0. So we can say that if I've decided to call 1 over n h, as n approaches infinity, h is approaching 0. One other thing is that if I've decided to call 1 over nh, one other thing I can say about this, if h is 1 over n, if I multiply both sides of this equation, well, actually, if I solve this equation for n by first multiplying both sides of the equation by n, and then dividing both sides of the equation by h, again, I'm just solving for n. What I end up with is n equals 1 over h. You see my h is looking like a lowercase n. That's why I'm using a big N here. So, so n is equal to 1 over h. So because of that, I can go back up here to this definition and kind of redefine this, or not redefine it, but just write the definition differently. I can say that this is the same thing as the limit as h approaches 0. So I can rewrite this definition just in terms of h instead of n, because as n approaches infinity, h approaches 0. And then of 1 plus, so I decided to call 1 over n h, so I can just say this is 1 plus h. And then raised to the power of n, which we just found, since I decided to call 1 over n h, n is equal to, wait, I'm not sure what I just said, but since I decided to call h, or 1 over n h, yeah, that's what I said, and that's what I wanted to say. Since I decided to call 1 over n h, n is the same thing as 1 over h. So this is another way to define the number e. So that said, and this is a really useful way for us to define the number e, because we are going to prove that this derivative is e to the x, and in order to prove it, we're going to use the definition of the derivative. So a reminder of that definition of the derivative. Definition of derivative, it's just that the derivative of a function is equal to the limit as h approaches 0, this is h approaches 0, of f of x plus h minus f of x over h. So we're going to use this definition. And look, in the definition, h is approaching 0. We're taking a limit as h approaches 0. So that's why it's useful to have e written in this form. So that said, here goes our proof. So we can say the derivative of e to the x is equal to the limit as h approaches 0, and we're going to use this definition of the derivative again. So f of x plus h, in this case our f of x is e to the x. So f of x plus h is going to be e to the x plus h. I'm just replacing my x with x plus h. And then again, my f of x is e to the x. So that's this part. And this is over h. Here's a little bit of one other little review just from algebra. Notice we're adding exponents here. That happens when we're multiplying two numbers with the same base. We add the exponents. So this isn't part of the proof. This is just a little reminder from algebra for what we're about to do. So this is the limit as h approaches 0 of, so I'm just going to rewrite this e to the x plus h in this form right here. So e to the x times e to the h. That's the same thing as e to the x plus h. And then we have minus e to the x, this is over h. And then this is the limit as h approaches 0. I'm going to factor out an e to the x because each one of these terms has an e to the x in it. And I'm left with e to the h minus 1 because there's like this invisible 1 here, right? If I distribute my e to the x, I'll just get what I started out with. And now I'm going to use my definition of e. So like now that I have this, I'm going to go, where's my definition? Here it is. Here's my definition of e. I'm going to use this. I'm going to replace my e to the h with this thing. The e in the e to the h with this. So, and again, notice this has limit as h approaches 0. This has limit as h approaches 0. So I'm good. So we end up with the limit as h approaches 0. And so I have the e to the x. I'm just bringing that down. Now this looks really messy, but the mess is worth it. This right here, I am going to put in place of this e right here. I already have the limit as h approaches 0 part, so I don't have to worry about that. So I'm just going to replace this e with this up here. So instead of writing e to the h, I'm going to have, and yes, this is a mess, 1 plus h raised to the power of 1 over h, right? That's just my e. That's just e. And then notice that this is all raised to the power of h. So I need to like say, okay, and then this is all raised to the power of h. So the blue part, that's just my e. And then I have the h hanging out there as a power. And then I'm just bringing down my minus 1. And that's what we have. And then this is all over h. So yeah, it's a mess. I'm going to, let's zoom back in so we can look at this, what we have here. And yeah, it looks messy, but watch this. So here's another little reminder from algebra, not a part of the proof. A to the m raised to the power of n is a to the m times n. So we're going to use this little rule from algebra because look, we have this a to the m to the n, like that whole format right there. And so we can just multiply 1 over h times h, and they end up canceling each other out, the h's. And so all we end up with is 1 plus h to the first power. So this is what we have now. The limit as h approaches 0 of e to the x times 1 plus h raised to the first power. That's just 1 plus h, right? And then minus 1. And this is all over h. See, I told you it was worth it. It was messy, but in the end, it's worth it, because look at the ones cancel. So now I have the limit as h approaches 0 of e to the x, and all I have up here now is an h, and I have an h in the denominator also. And look at the h's cancel. And now all I have left is e to the x. I don't even, like, there's not even an h to plug 0 into. So all I have is e to the x. And I am done. And the math person's way of saying I'm done, I showed you what I said I was going to show you, is to write QED. It stands for the Latin phrase quod erat demonstrandum. Do not repeat my pronunciation. I'm sure it's horrible. But yeah, you can write this QED. That just means you're done. So happy math. I will be putting up more proofs during the rest of this week. Bye.